Look at a function. Let's say on page 218, let's say problem 24. Yes. So the next section, which is 2.2, I'm going to call it the way they call it. They entitled it second derivative test, using second derivative, blah, blah, blah. I don't like that definition or that title, but I'm going to use it. I'm going to say second derivative test. We don't even know what the first derivative test is because I didn't name it yet. I will name both and I will explain both again. But I need the concepts first. Okay, so let's look at the following function, 24 on page 218. In this problem, we are asked to graph. And now I agree, but we have to go through other steps before we graph. And the function is f of x equals 3x to the fourth plus 4x cubed. And you could say, that's very easy. It's a polynomial function, degree 4. I can plug it in the calculator and I'm done. True. That's correct. However, that's not why we're here for. So, first step, domain. So now we want to graph this function. That's the target. Domain. And you can say, you just said it, it's a polynomial function, it has to be defined everywhere. Good, it is. Number 2. X-intercepts. How do I find the x-intercepts for any function, including this one?
You said f of x equals 0.
Excellent. Y equals 0 or f of x equals 0. 3x to the fourth plus 4x to the third equals 0. Very good. What is the degree of this polynomial? I have to have 4 solutions, even if they're all the same. I have to write 4 solutions. Okay, so I'm solving this equation. I will factor out x to the, very good, and then I have 3x plus 4 equals 0. Can anyone give us 4 solutions? Even if some of them are the same. 4 solutions, degree 4. Fourth degree. Yes, 3x equals 0, correct?
Negative 4 over 3.
Excellent. Step number 3, y-intercept. In this case is redundant because I have to make x equals 0 and I get the same thing, y equals 0. Step number 4. Critical numbers. How do I find the critical numbers of a function? Very good. F prime of x equals 12x to the third plus 12x squared. I found the derivative, and now what is next? After finding the derivative, I must solve the equation. So remember, critical numbers come from f prime being undefined, which is a waste of time for this function y. It's always defined. And the other one is from f prime of x equals 0, which means 12x cubed plus 12x squared equals 0. I have to identify the degree so I don't forget how many solutions I need to come up with. Degree 3. Third degree, 3 solutions. I am never ever allowed to divide both sides of an equation by the variable, but I'm allowed to divide both sides by 12 to make my life easier. I get x cubed plus x squared equals 0. Same equation. And now I will factor out x squared and get those three options as expected. Two of them are,
0.
and the last one is,
-1.
very good. Now I can get my table going. And now we are going to have a complete table. Up until now, we did not have a complete table. Now we have a complete table. Here's what I mean by a complete table. X values, first derivative, the function in the middle, and the second derivative as the last row. Ready? We already established the domain is negative infinity to infinity. We also established, we didn't finish, I'm going to add more, but we also established that the function has 0, 0 as the x and y intercepts, and -4/3 0 as the other x-intercept. So for the function 0, 0, -4/3 0, I want one more thing about the function. I want something here and something here, which will be our fifth step, and behavior. But this is not done like we do it in algebra, because we have a very important concept that we discussed. It's called, yes, as x approaches infinity from 3x to the 4th plus 4x cubed. And later on, the other one with minus. We don't discuss the end behavior like we used to. Now we have the concept. Okay. Which of these two quantities or terms is the most powerful when it comes to infinity? Right, so completely disregard this one. Imagine that you plug infinity in here and give me the answer. Very good. Again, the same question. This is the most powerful. Imagine you replace x by negative infinity and give me the answer. Therefore, I went back and I filled in everything I can find from the function, about the function itself. There's nothing else I can find. Yes, please.
X equals -1 from the, is that the y-intercept?
You mean this one here?
Or the third degree from when we found f prime of x?
Yes, I didn't get to the f prime yet. I just filled in the f of x first. So now I'm doing that. That's the next step. Thank you. Very good point. Okay. So now, once we finish with the function, we can discuss the first derivative. We have two things that we know about the first derivative. I know this, and I know this. 0, and at -1 is also 0. Now I need to study the sign of the derivative. Here's the derivative. This is the derivative. Please plug in a number like -5 and tell me the sign. -5.
Negative.
Exactly. No questions. Now this is a little bit difficult because I have to plug in -0.5. So let's put it in. 12 in parentheses -0.5 to the third power and plus 12. Tell me what you get. I got positive 4.5. So obviously positive. And please plug in a number to the right of 0, like 10. And tell me what you get. It's a silly question. Positive. Perfect. Very good. At this point, I have to make sure that these two rows work well together. That's the moment in which I test my work, and that's the moment in which I find mistakes, if there are any. Ready? From positive infinity to 0, what does the function do? Is that supported by the sign of the first derivative?
Yes.
So far, so good. At this point, I have to find this value here. I have to plug in -1 in the original function. -1, -1, so it's 3 minus 4. -1. Good. So I know it's kind of squeezed. Look how much space I have here and how little I have here. So I didn't plan correctly. But that's good enough. I think you're... So between 0 and -1, what does this function do? Between 0 and -1? Decreases, right? From 0 to -1. Is that supported by the sign of the derivative? Yes?
Yeah.
Very good. Between -1 and 0, what does the function do? Is that supported by the sign of the derivative?
Yes.
From 0 to infinity, what does the function do? Is that supported by the sign of the first derivative? The two rows, the first derivative and the function, work well together. Second derivative. And why? Do I still have time? Yes. Okay. Second derivative is number 6. F double prime. So let's summarize for a moment. What does the first derivative say about the function? It tells us whether the function has the maximum in. It tells us whether the function is increasing or decreasing. Agreed? Good. We don't know what the second derivative will say. Let's calculate it first, and I'll tell you what it says. So here's the first derivative. So this will be 36 x to the second power plus 24x. Like with the first derivative, we are going to set it equal to 0 only. What is the degree? So I know how many solutions I have to find. Degree is 2. I have to find 2 solutions. Very good. And 36x squared plus 24x equals 0. I will simplify by 12, first of all, to get rid of that. So I have 3x squared plus 2x equals 0. Yes, I factor out the x, and I get 3x plus 2. And I do have 2 solutions, x equals 0 and x equals -2/3. Of course, it has to happen. Where will I plug in the -2/3? I have to redo my chart. I don't have enough room. It's because I got -4/3 and I got -1. I got -2/3 in a tiny little space. So I'm going to redo my chart. My apologies. You can determine all these numbers before you start the table. So maybe in the future we'll do that. But I still want to summarize my information immediately so it doesn't go away somewhere. In thin air. So there's not going to be anything else. This is it. -4/3, -1, -2/3, 0, and infinity. I needed more room in the table. I'm copying the rest. Okay, so I'm copying the arrows also. I want to leave some room here for this. Let's see what happens at negative 2/3. Let's find the value. I need this value here. So I have to go back to the function and plug in negative 2/3. I should have put in the function. I recommend that from the very beginning. Put the function in so you can get the values quickly. So I put the function in 3x to the 4th, 3x to the 4th, and then plus 4x cubed, plus 4x cubed. And then I need to plug in negative 2/3. In parentheses, negative 2 divided by 3. Okay, so let's see what we get. I got negative 0.6. Wonderful. So negative 0.6. Very good. So now, indeed, decreasing, decreasing, increasing, yes, increasing and increasing. And now finally I have to study the sign of the second derivative, and finally I'll tell you what that means. Okay. So, and we had 0, of course. We had 0 and negative 2/3. 0 and negative 2/3. Okay, so let's look at the derivative. This is the second derivative. I prefer this. With a 12, without a 12, it doesn't make any difference. Or this. So let's plug in a number to the left-hand side of negative 2/3. Like negative 10. 36 times 100 minus 240. Is this a positive? Indeed. Of course it's a positive. Now again, of course, more difficult. Plug in a number to the left of 0. This is negative 0.6. So negative 0.5. So negative 0.5 times 36, 36 times negative 0.5 squared plus 4. I normally, with my calculus class, I don't do this. I will study the sign a different way, but with you, that's good enough. I don't want to torture you with more, because it's the same thing, that's all. We got positive, of course. We got negative. It has to be negative.
Negative?
Yes, it's in between solutions is the opposite sign. Yeah, so let's do that together. It must be, because it's quadratic.
Okay.
So between solutions, if it's, always remember, if it's a quadratic function, which it is, the second derivative is quadratic, and it has a minimum, and it crosses the x-axis in 2 points, between solutions, it has to be under the x-axis. So between solutions, it must be negative. If it's a minimum, if it's a maximum and it crosses between solutions, it has to be above the x-axis. So let me show you with the graphing calculator. Okay, so put in y equals. In this case, we have 36x squared. And then we have plus 24x. So now we can do the whole thing. I can plug in negative 10. You probably did when we know it's positive. Oh, yes, of course. Okay, so when you plug in negative 10, of course you get positive. When you plug in negative 0.5, you have to get negative. When you plug in 10, you have to get positive. Because it has a minimum and it crosses the x-axis. So therefore the signs, yes, I am. Okay, so what am I doing? Okay. So this must be negative and this must be positive. Okay. We know what we learned from the first derivative. Increasing, decreasing intervals, max, min. What does this second derivative say? The second derivative tells us whenever the second derivative is positive, the function is concave upward.
So it's above the x-axis.
No, it's opening up.
Okay.
Whenever the second derivative is negative, the function is concave down. Whenever the second derivative is positive, the function is concave up. But now, what does this point represent where the second derivative changes sign? From opening up to opening down.
That's the number.
Inflection point. From opening up to opening down. So from opening up to opening down. This point is not a max-min, but it's called inflection point. Or vice versa. From opening down to opening up. Still an inflection point. So this point, this is an inflection point. From opening up, this is the symbol that I highly recommend you use. Or invent your own, I'm fine with that. And opening upward. This point is another inflection point. What is this point? -1, -1. What kind of point is -1, comma, -1?
Inflection point? It's a min.
Exactly, because the first derivative changes sign from negative to positive. So min. What kind of point is 0, 0? How come that 0, 0 is not a max or a min?
It's just one of those numbers.
Because the first derivative does not change sign. That's why 0, 0 is an inflection point, because the second derivative is 0 and changes sign, or undefined and it changes sign. Let's graph this. Yes, and then we'll put the summary. Yes.
For the -0.6, it's increasing on the left.
It's increasing all the time. Increasing all the time.
No,
From
like
-1 up to -0.6 up to 0.
Correct, but where you circled it and put inflection point and
0,
f of x.
0.
No, but for f of x, when you circle
This is f of x.
Right, but -0.6.
Also an inflection point.
Correct, but
So
increasing
this comma
increasing-
this is an inflection point, and this comma this is an inflection point. There is an inflection point when the function is increasing, and there is an inflection point when the function is decreasing. Oh, when the function is decreasing and when the function is increasing.
So an f double prime
Yes?
is since it's increasing then decreasing, decreasing then increasing.
No. F double prime has nothing to do increasing and decreasing. It only tells us the shape.
Okay.
It tells us whether it holds water, we say, or it does not hold water. Concave upward or concave downward.
Now with f of x though, because it's increasing, increasing, increasing in between your inflection points, how can you say those are 100% inflection points?
Mandatory. If the second derivative changes sign, has to be an inflection point. We're going to graph it right now.
Okay.
So after we graph it, we'll summarize everything we discussed tonight, because there are two things that I didn't explain. I mean, I did, but I didn't name them. Okay, let's graph. You understand that all the information is in here.
Yes.
I don't care about the pages and pages of work, like 4 pages of work, because once I summarized everything here, that's where I look. Ready? I have to plot the points first. It's kind of hard, -4/3, comma 0, but it's this point. Then I have to plot -1, -1, which is this point. Then I have to plot, this is even harder, -2/3, comma -0.6. Oops.
Can you bring it up just in here?
Oh, yes, of course, of course, of course. I'm sorry. And then 0, 0. Yes, so let's do this again from the beginning. Sorry about that. -4/3, 0 is this point. Maybe I should create a bigger unit because it's so tiny. So I'm going to say this is -1. This is +1, +1, +1. Okay? So negative 4/3, 0, if this is, I'm going to say here, negative 4/3, 0. Negative 1 is this point. Can you see? Then negative 2/3, negative 0.6. And 0, 0. Tell me when you are ready to follow this step by step with me. Ready? Okay. From positive infinity, decreasing, opening upward to this point. From positive infinity, decreasing, opening upward till this point. Continues to decrease, continues to be upward till this point of minimum. Continues to decrease, continues upward. Because the unit is so big, I'm going to have to make some adjustments here. Because the direction is not, it has to be smooth. It's a continuous function. If I have to twist my wrist, that something is not right. Till the point of minimum, where it's still opening upward, but now it's increasing to this point of another inflection, of a first inflection point. Increasing, opening upward till the inflection point. Still increasing, but it opens downward till the other inflection point, 0, 0. An inflection point, increasing, opening upward towards infinity. This is our function, which was, have no idea, 3x to the 4th plus 4x cubed. Everything is in this chart. You understand? Let's read the chart one more time. The function is decreasing, opening upward till this point. Continues to decrease, still opening upward to the point -1, -1, which is a minimum. Still opening upward, but now it's increasing to the point -2/3, -0.6. Where it changes concavity, because it's still increasing, but it opens downward. Till this point of inflection, 0, 0, where it's still increasing, but this time it's opening upward. And that's the graph. Oops, I'm sorry. Sorry, I got carried away.